strike simulated houses and power lines to understand what happens when it hits. The rocket launch provides a more controlled experiment than anything Ben Franklin could have imagined.
Well, we do similar things. He didn't think his kite was going to get struck, and he thought that if it was going to get struck that he wouldn't get hurt. So he was wrong there. If the kite had been struck, he probably would have been killed, as have many people flying kites.
They load a rocket and launch it into the belly of a thundercloud. From the rocket's tail, a spool of copper wire unwinds, creating a path for the lightning to follow.
There's a level of excitement and tension before you push the button, and then there's a level of holding your breath for 2 seconds when the rocket goes up that's unlike anything else. And success feels real good because we only make it happen 20, 25 times a summer, so every one is a big deal.
It's like a rocket-powered lightning rod. Once the wire is shot up into the air, the lightning hits it. In an instant, the electric current of the bolt moves down the wire, disintegrating it into a green vapor.
What flows down the lightning at 50,000 amps is the same thing that flows in your wall at 10 amps.
The temperature of a lightning bolt is more than 50,000 degrees Fahrenheit, 6 times hotter than the surface of the sun. All that heat and light is generated by uncounted numbers of electrons being forced to move. An atom's nucleus has a positive charge. Electrons orbiting the nucleus have a negative charge. When electric current flows, electrons are torn from atoms and move freely.
Electricity is the flow of electrical charge, and most of the charge flows as electrons moving.
Whenever there's an oversupply of electrons, an object develops an overall negative charge. Nature balances things out with equal positive charges somewhere else. The potential difference between the charges is measured in volts. Electric current, anything from static electricity to lightning bolts, is electrons moving from negative to positive.
It seems like it's easier to make sparks and lightning than not to make them. Anytime you have two dissimilar materials rubbing together, you get sparks.
The path that leaping electrons follows depends on the material they flow through.
The human body certainly will conduct current, but not a lot. Not like a piece of copper.
Copper has a lot of loosely held electrons, so it's a good conductor. The electrons of clay and rubber are too tightly bound to their atoms to conduct electricity. They're said to be insulators. How electrons begin to move in the first place is a result of a force of nature called electromagnetism. Our whole technological civilization exists because electricity can make magnetism, and magnetism can make electricity.
It goes back to the fact that we have two kinds of forces that are present that we call electricity or electromagnetism. And those two forces are the electric force and the magnetic force. The fundamental charges are a positive charge and a negative charge.
To see these forces at work, head north and look up into the night sky. Basically, the northern lights are the result of high-energy electrical currents from the sun that are caught and guided by the Earth's magnetic field. There's electricity out there.
5, 4, 3, 2, 1. And we have liftoff of the Space Shuttle Columbia, continuing space research through tether satellite technology.
On February 25, 1996, NASA and Italian researchers made a bold attempt to harness the power in the atmosphere. They generated electricity with a satellite on a wire.
Good work. Let's make sure we stay that way. Understand.
The mission was part of a new experiment of tethering satellites in space.
Attitude verification, 3-14. Go ahead.
The experiment was based on the simple principle that when you move a conductor through a magnetic field, electrons start to flow. This generates an electrical current that can flow through a circuit. The satellite was thrust into space using small gas jets, and the 13-mile-long cable began to unreel.
If you put a wire inside of that tether, you now have a moving wire that moves across a magnetic field. That magnetic field in this case is the Earth's magnetic field, and the motion is the motion of the space shuttle moving at very fast, high velocities, orbital speeds.
Things look fine down here, Jeff.
The moving wire in the Earth's magnetic field generated 3,500 volts, enough energy to power a space station.
Okay, we see the tension go way down, but the tether's still going out fine. Very slight lateral oscillation.
The tether was clearly visible from the ground. It was one of the biggest man-made objects ever sent into space. For 5 hours, the tether swept through our planet's magnetic field, generating more and more electricity.
At the boom. The tether has broken and is going away from us. Get it on the TV, Claude. Please get it on the TV. The tether has broken.
Copy.
Trying to photograph it floating away from us.
Looking back, we quickly saw that, in fact, the tether had broken. This was it's a big shock. It's kind of an empty feeling in the pit of your stomach when you look and you realize that there is the tether moving away from us at about 80 feet per second, and you just wanted to reach out and grab it.
The wire was generating so much electricity that a spark jumped from the wire to the satellite deployment system and burned through the tether. The $440 million experimental satellite just drifted away.
Yes, sir. Well, those are some tether dynamics we did not want to see.
Well, we have demonstrated that you can generate a lot of electricity with tether, and unfortunately we've also demonstrated that you can use tethers to launch a satellite into a much higher orbit.
NASA will try the experiment again because it could lead to a new, more reliable power system for space stations.